All right, two things to cover today. We'll talk about Bernoulli's principle. Bernoulli, once again, is a mathematician, but also science. He worked in both realms. When you talk about Bernoulli's principle, it's used quite a bit in our life. Okay, as we deal with, if you ever have driven on or flown on an airplane, you're dependent on Bernoulli's principle. As the velocity of a flowing fluid increases, the pressure of the fluid decreases. So if we increase our velocity of a fluid, now a fluid could be a liquid or it could be a gas, because the fluid is anything that can be a flowing idea, anything that could flow, which is a liquid or a gas. If we increase the velocity of it, we decrease pressure. Johann Bernoulli, he has some good hair, man. They all had good hair back then. He was born in 1667, died in 1748. Was one of the 8 Swiss mathematicians produced by a remarkable family over a course of 3 generations. A professor of mathematics of the Gregorians, and later at the University of Basel, Bernoulli was one of the most successful teachers of his times, able to arouse in his students the same passionate love in mathematics that he felt himself. Johann shared the discoveries of his older brother Jacob, but wrote on the even wider range of mathematical topics, even though the two were bitter rivals. For Johann was jealous of and resentful of Jacob's mathematical brilliance. They maintained an almost constant exchange of ideas with one another, as well as such contemporaries as Leibniz. Okay, Gottfried Leibniz, along with Sir Philip of Isaac Newton, they're the ones that developed the idea of calculus. And why calculus was developed? Because they needed to explain physics somehow. Bernoulli was one of the first mathematicians to realize the surprising power of calculus to apply to the tools of great discovery of problems. His contributions greatly enriched calculus, and Bernoulli helped make its power appreciated in Europe. So he was a mathematician, but scientifically, Bernoulli's idea is basically how airplanes fly. Okay, without this idea, airplanes don't fly. When you have fluid going through a pipe, okay, when you have fluid going through a pipe, you have velocity of the fluid, but you also have this pressure. Where the pressure is measured is on the outer walls. So you feel this pressure on this outer wall. It's pushing outwards. Okay? Think about a hose. When you have a hose, okay, the spigot's turned off, your outside spigot turns off, you can push in the hose pretty easily. Okay, there's no water in there. But if you turn the spigot on, all of a sudden it will fill up with water, and you start feeling the pressure of the water on the outer edges of the hose. If you would take a needle or a nail and drive it through the hose, water would start spurting out. Okay? Very similar to a vein in your blood. You have pressure, you have your veins that keep your blood flowing through in a orderly manner through your body. But if you break one of those veins, you have pressure there. If all of a sudden you lose pressure on that vein, you start punching a hole in it, you're going to have blood spurting out. Okay, I try to give blood as much as possible, and this is the first time this has ever happened to me. It was the weirdest thing. I gave blood, and after you give blood, you put your arm up and you put gauze over top of where they took the blood out. Okay, and after a minute, they say, okay, you can put your arm down. Well, I'm watching this, and all of a sudden there's like, usually it stops bleeding. All of a sudden there's blood starting to trickle down a little bit right here, and it's getting on my fingers, and the guy's like doing something else, and I'm saying, okay, we're having an issue here because I'm still bleeding. So he said, put your arm down, and I took the gauze off, and it starts spurting out a little bit. I went, this is not good. This is not good. Well, this is Bernoulli's idea, though. I'll blame it on Bernoulli. See what entertainment you get in this classroom? Okay, as the molecules have velocity, they have to have kinetic energy. Anything with velocity, we have kinetic energy. Each one of those water molecules has kinetic energy of 1/2 mv squared. Because the water molecules have, or whatever it is, has a mass to it, and it's traveling at a velocity, which means you have kinetic energy. But if you put a stop at the right end, if you put a stop here at this end, okay, the fluid will build up and create pressure. Okay, once again, your hose at home. Okay, you turn it on and you have the nozzle there that's screwed on, hopefully, and hopefully nice and tight. Okay, so you don't get your feet wet, or it doesn't spray out and get your shirt all wet. So water starts flowing through the hose, and it hits the nozzle and it stops flowing. All of a sudden, it builds up this pressure. This pressure is your potential energy. So we have transferred from kinetic energy, the water molecules moving with kinetic energy, to where it stops. It has the potential to keep moving, but something's stopping it from keep moving. So it has now potential energy. The pressure is that potential energy. If no energy is lost to the walls, then this kinetic energy plus this potential energy has to still equal value 0. Okay, if I'm not losing any energy, I need to have conservation of energies. Yeah. Some of this energy is lost due to friction and thermal energy. You're going to lose some because it's not ideal. Water molecules will have friction between them. Okay, you'll have some thermal energy that's lost or gained through the walls of the hose. So if we take a look at a hose, with or without the nozzle, okay, we have our green hose. Okay, we have this green hose that's all coiled up here. Got this silver end here. We turn the water on, we have no nozzle on. So water just sort of flows out. Okay, just sort of flows out. But if you put a nozzle on, or you put your thumb over top of the hose, the edge of the hose. Got the hose here, and you put your thumb down there, which restricts the amount of area there where the water can flow out. Okay? Or you put a nozzle on. If you put a nozzle on, the nozzle is very, very small. And you restrict the area. And you start squirting the hose with the nozzle. How far does the water go now? Does it go a little bit further than just this right here? Yeah, goes a little bit further. You put this nozzle on, you restrict the area, so we still have this green hose here. Still have the end, but now we're going to put a nozzle on this. And we're going to start restricting the water, restricting the area. So my area gets smaller. And all of a sudden, I'm able to shoot out as far as I want and try to hit my brother or my sister or my cat or my dog. Because now they can start running, but you can now squirt a little bit further. Where if I just have this right here, I can't get anybody wet because it's just going like this, blah, blah, blah here. If I get this here and I get a nozzle and I start spraying it and I restrict that area, I could get it going further. Well, what's happening here? If we take a look at Bernoulli's idea, the velocity of the fluid increases, the pressure of the water decreases. Well, what we're dealing with here is the idea of our velocity. Our velocity is increasing. So when I restrict my area, when I restrict the area, velocity increases. When I restrict my area, my velocity increases. When my velocity increases, okay, water molecules turn into projectiles, we have a greater velocity. So what we now have is we have trajectory motion. We have projectile motion here. My velocity has increased. When our velocity increases, objects go further. So the greater the velocity, the further the water molecules will travel. So when we get a nozzle there, when we put a nozzle in there, we restrict our area. Okay, so your nozzle will restrict the area. When I restrict the area, my velocity will increase. So as the cross-sectional area decreases, the velocity will increase. If the velocity increases, the pressure will decrease. So as the cross-sectional area is decreased, the velocity will increase. But the pressure then will decrease due to Bernoulli's ideal. If we take a look at what is called a Venturi meter, okay, it's called a Venturi meter. What you have is you have water flowing through. We restrict the area here, and then we increase the area again, the cross-sectional area. When you measure pressure in pipe flow, okay, when you talk about pressure in a pipe flow, what you'll see if you go into any type of system, mechanical system, and you have a pipe flow, what you're going to see is you're going to see a pressure gauge. And that pressure gauge is going to be threaded or screwed into the wall of the pipe. And what you'll see is you'll see pressure there. Your car tire, okay? You have a little nozzle that comes out of your car tire, out of the side wall. You could put your little pressure gauge on that car tire and measure how many pounds of pressure you have in your car tire. You could do it, or maybe your parents do it for you, your dad does it for you. Okay, but it's on the side of the wall. It measures the pressure. If we take a look at a Venturi meter, you have water that's flowing through here. This here measures the pressure. What you'll see is you'll see a certain height here, which will measure the pressure. As water goes through here, as water starts to go through here, we start decreasing the cross-sectional area, which means the velocity will increase, but the pressure will decrease. So when the area decreases, the velocity increases. And the pressure will decrease. When this area decreases here, velocity increases and the pressure will decrease. So if I measure the height here, this is my pressure. When I start restricting my area here, my area gets smaller. My velocity has to increase, and the pressure will decrease. So my pressure on the wall is not going to be as high compared to over here. Here I have a higher height, here I don't have a higher height. And then when we get to the very end here, my area increases again. So my area goes up, my velocity will go down, and my pressure has to go up then. So my pressure is back up to here. What I always remember here is when my area gets smaller, my velocity increases. The reason why is you have a bottleneck. More people or more things have to get through this. More things have to get through, so I have to go faster. Now, and this is we're in construction time and out in the roads, and we start running into traffic jams. In theory, and you don't do this. This is something you don't do. It's dangerous. You want to keep safety in mind. But an analogy I could throw out as, okay, you got 2-lane highways coming here. You got 2-lane highway. Mile ahead, it goes down to 1 lane. So basically, you're restricting the area that cars can go through from 2 lanes down to 1 lane. Okay? You are to slow down and use caution. Everybody should go down to 30 miles an hour or 25 miles an hour and slow down and use caution. Okay? And that's what I'm saying here. You do that. But in theory, if everybody put their foot on the gas pedal and got into the 1 lane, you would have no bottleneck of traffic because all the cars are going faster through that bottleneck of traffic. Just very dangerous, and it's something nobody ever wants to do. But in theory, that's the idea that you have here. Okay? You follow the laws. When you ask to slow down, you slow down in construction zone. You do that. But in theory, using this idea, the Venturi meter, when you restrict the area, if everything just goes faster, everything can go through. And then you don't have a 2-mile long line of traffic to get through there because everything slows down. Dangerous, you don't do it. Cross-sectional area and velocity are inversely proportional. They are inversely proportional. V1A1. Oh. That's wrong. V1 over A1 is equal to V2 over A2. If we take a look at an airplane wing, what happens with an airplane wing? Well, you have this air that starts flowing into the airplane wing, okay, runs into the airplane wing. You have a bubble on top here, a rounded edge on top. When you're traveling, when the air is traveling or the wing is traveling through the air, what this does here, this airfoil that does here, this speeds up the air. So the air going over top of the airplane wing gets sped up. This just maintains a velocity or slows down a little bit. but this speeds up my air. If this speeds up my air, my velocity increases. If my velocity increases, pressure decreases. If velocity increases, the pressure decreases. Well, if I take a look, my pressure on top of the wing is smaller. I have two pressures here. I have pressure on top and I have pressure on the bottom. My pressure on the bottom is greater than my pressure on top. So my pressure here is greater. If my pressure on the bottom of the wing is greater than my pressure on top of the wing, it's going to make the plane lift. Because my pressure here is greater on the bottom pushing up than my pressure going down here, which means my force on the bottom, or my force on the bottom, is greater than my force on top. What this is called lift. It pushes your airplane up. It makes your airplane fly. It makes it lift in the air. This is Bernoulli's principle. Airplanes fly by Bernoulli's principle. On the back of a car, you have an airfoil. It's like having an airplane wing attached to the back of your car. It puts this in the airplane wing and turns it over, which means my pressure on top, is going to be greater than my pressure on the bottom. If my pressure on top is greater, it's going to force it down onto the road. If you look at NASCARs. They have this airfoil on the back. What they're trying to do is increase your normal force. Because when you increase your normal force, you're increasing your force of friction. When you increase your force of friction, you have better traction on the ground. So when you increase this force normal, this increases force of friction. Now, there is a balance between how much they want to increase by. The reason why is if you increase your force of friction too much, it's going to wear your tires out too quickly. And then you're having to go change your tires too many times. So there's a balance, there's an engineering balance between how much force of friction do I want. Because ultimately, they want the cars to be as light as possible. They don't want to be like a truck in the wintertime that's not four-wheel drive that has to put sand bags in the back of the truck to give it more weight in the back of the truck to increase the force of friction to get better traction in the snow. They don't want to have to add more weight to the car. They want to keep the car as light as possible, but they want to still be able to increase your force of friction. And how they can increase the force of friction is by putting this airfoil on there, because that's going to increase my force normal. But they don't want to increase it too much, like I said, because then it's going to wear your tires out real quick. They're going to go 2 laps around the track and have to go get new tires. take a look at a buoyant force problem. You have a raft with a length of 3 meters, a width of 1.5 meters, and a thickness of 12.12 meters. The density of the raft is 750 kilograms per meter cubed. It's placed in a river. How far below the water surface does the bottom of the raft sink? So you put this raft in the water, and some of it goes below the water, not all of it. We have a thickness of 0.12. We have a length of 3 meters, and we have a width of 1.5 meters. We want to know how far this raft sinks when we throw it in the water. We want to know this value y, or x. What's that distance there? We have the density of the raft. And we have the density of water. Well, if we take a look, what we have is we have a buoyant force that we've talked about. We have a buoyant force that can be calculated by density of fluid, our density of fluid times gravity times volume of the object, but this is submerged. Not the entire raft is being submerged here. But if we take a look, the amount of submerged the volume of the object submerged is equal to 1.5 times 3 times this distance x. Okay, so we have 4.5 x. That's the volume of our object. This buoyant force is the force that's pushing upwards. We have still the force of gravity that's pushing downwards. Well, for the object to stay where it's at, what has to be, it's not falling down any further, it's not hopping out of the water. What has to be true about the force of gravity in the buoyant force here? Force of gravity is pulling it down, buoyant force is pushing it up, and it's maintaining a certain level in the river. They have to be equal. So this force of gravity has to equal the buoyant force. Well, how do I find the force of gravity for my object here? Well, the force of gravity is equal to its weight, which is mass times gravity. We know what gravity is, but the mass, how do we know its mass? Well, density is mass divided by volume. So mass is equal to density times its volume. Well, the density of this object is 750 kilograms. The volume of this object, now we're talking about the entire object here. The volume of this entire object we can calculate by 3 times 1.5 times 0.12. So the mass of this object is equal to what? 750 times 3 times 1.5 times 1.12. What do we get for the mass? Grace, what do you get? 4,050? You good with that? Yes, no, maybe so? $405? Yeah. There you go. So we have 405 kilograms. That's the mass of this object. So we can now find the force of gravity, which is 9.81 times the 405. And we can find the buoyant force, which is the density of the fluid, 1,000 times 9.81 times my volume, which is 4.5x. And these two values have to be equal. And we can set them equal and set them solve for x. What do we get? 0.09. So we get x is equal to 0.09. So that's how deep underneath the water that raft will float or will go. Now, what's the rest of this week going to look like? We have homework problems. Now, the homework problems are not going to be collected. I put solutions on Classroom. Okay, so you could do some, it's just extra homework problems, extra problems for you to do. Okay, they're not going to be collected, just extra practice for you. You have solutions that you can work for. Okay, I have a review sheet here for you. Solutions to the review sheet are also on Classroom. Okay, on Friday, we will have a test over Chapter 8, but it will be open note. Okay, so your test will be open notes. So as much as you can get done here, okay, this is part of notes here. Homework, worksheet, review sheet are part of the notes. So get this stuff done. Okay, work towards that. We'll spend tomorrow, answer any questions that you have tomorrow. But Friday we will have an open note test over Chapter 8. All right, adios. Have a good day.